These are some ancient structures. Take a look at them carefully. Although they may seem vastly different from each other, they all have one thing in common: the way they were built. These very solid structures, that pyramid shape, allow them to be protected from the elements. As the outer core was eaten away, the deepest parts were protected. If you tried to make something other than a pyramid shape, over time chips would have formed in the concrete and then it would have collapsed eventually. If you want to speed the process up, put it in the ocean and the currents will batter it to pieces. This is where Roman concrete stands out. Their structures have a more modern aesthetic to them. It's more rectangular in shape, they have isolated pillars, engravings and designs etched into the stone, and somehow they are standing for thousands of years. So how did they do it? What did they do differently from us in modern times, where if we don't do proper maintenance in a building, within 100 years it will be leveled to the ground? To solve this mystery, the first thing that we need to do is to analyze the concrete. Here's a piece of Roman concrete. Within it, you can see some discernible features. Test them and you'll see what the components are made of. That white lump there is calcium hydroxide, otherwise known as slate lime. The other smaller dots are either small stones or rock fragments. The blacker ones is tuffra or volcanic rock. This particular combination has a very unique quality. If it gets damaged, it can heal itself. If there's a crack that is formed within a structure, within a matter of weeks it will repair itself. So seeing that we know all the ingredients, we can make it, right? No. Even if you combine all of these things together, it still wouldn't work. The reason why we know this is because we have tested it. The biggest problem is that it doesn't contain that self-healing property that the Roman concrete had. And this is despite the fact that we possibly did it better than the Romans did. They used large chunks of volcanic rock. Those lumps of lime within the structure is because of an improper mixing technique. They used the rubble that they had at hand to put inside of their concrete. We wouldn't do any of these things. We had better materials to work with. So then why is our concrete inferior? Our first clue came when we x-rayed rock that has been in the water. When the results came back, we found these crystal structures. And then in 2017, researchers have found those crystals formed because the seawater had interacted with the rock. There was a chemical reaction that was occurring, causing the rock to form more crystals and becoming harder and harder. The volcanic rock that was inside of it contributed to that chemical reaction, allowing the concrete to get tougher even though it had been cured for decades. That was one mystery solved, but a problem then presented itself. That chemical reaction occurred only in seawater. There is no seawater near the Pantheon, the Colosseum or Roman aqueducts. So then what then were we missing? Professor at MIT for Civil and Environmental Engineering, Dr. Ahmed Masik, was wondering the exact same thing. He re-examined the concrete, and over time he kept looking back at those clumps of lime and began wondering, was that intentional or a mistake? You see, when we use lime, the first thing that we do is put water in it, allowing it to heat up, and it looks like this. As the lime interacts with the water, it brings it up to 120 degrees Fahrenheit or 40 degrees Celsius. As you keep stirring it to get a more even mixture and allowing it to cool down, you are left with a smooth paste that you can use. Professor Masik wondered if the Romans did that exact same process. So he tested it. He found that the Romans did not use the process that we did, by first mixing it in water and then putting it into the aggregates and mix everything with water. What they did was take the dried lime and put it into the aggregate. Then they mix everything with water. The chemical reaction that heated up the lime occurred during the mixing process. That caused two things to happen. First, it allowed the mixture to set faster, and second, it caused small lumps of lime. When Dr. Masik and his team tested it, they found that it had similar traits to the Roman concrete. They were able to replicate that self-healing property. So what were we missing? What happened was, as water got into the rock, it interacted with those clumps of lime, dissolving it and then recrystallizing itself, sealing the crack off, essentially healing the rock. Every time it rained, it allowed the Roman structures to be healed, and this process has been going on for centuries. Here's the best part. The concrete that we produce now can naturally absorb CO2 from the atmosphere. The process isn't very quick, but it does occur. Researchers have also found that basalt can even absorb CO2 more efficiently, possibly even turning it into a solid matter. What is basalt? Volcanic rock. The Romans were controlling CO2 long before we were. We knew that Roman concrete could have lasted for thousands of years, but we thought that we knew better than they. Those little lumps of lime were overlooked because we thought the Romans were making a mistake. Our own hubris caused us to miss something for decades now. But at least we got there in the end. This discovery is no doubt going to change the way that we do things. One simple adjustment can fix a problem that we have been coping with for decades. Thanks for watching.